All right, we're solving exponential equations, which if you're thinking, well, how is that different than an exponential function? It's not. But the reason we kind of put it in the terms of equations now is we're going to do stuff like this, where it's like, hey, listen, 2 to the x power is equal to 2 to the 5th power. Now, if I were with you today in class, here's what we would have done is I would have said, hey, let's take a look at that. And what would you assume that x equals? And take a look at that. What would you assume x equals? And based off of what you found here and here, how do you think you could solve that? And then we would have talked about this, and we would have tried a lot of these together. We would have hopped over here and done some reading, and then, yeah. So basically, we're just going to look at these kind of one by one. So if you were to look at this and go, okay, 2 is being raised to the x power. It's up there. 2 is being raised to the 5th power. And this side of the equation is exactly equal to this side of the equation, meaning they're the same exact thing. Then x must equal 5. It would only make sense for it to equal 5, right? Because if I were to write this down, if I wrote 2 to the 5th equals 2 to the 5th, is there anybody out there who's going to go, I disagree, I just don't think that's true? No, of course that would be true. So that is how that would work. So then slide over here and go, okay, well, in this scenario, it must be that that's 2 on the bottom, that's 2 on the bottom. There's nothing else over here on the bottom. Kind of got ahead of myself a little bit. Nothing else over here on the bottom. Nothing else over here on the bottom. So, okay, they both have exponents. It must be then that this, x plus 1, equals 6. Yeah, that's how it would have to work. So again, x is 5, so it's just kind of a little bit of a coincidence that they're both 5. But that's the concept, is that because this side is identical to this side, we can basically ignore their bases. In fact, I'm going to kind of write that. We're going to ignore the bases, and we're just going to isolate the exponents. And we did that here. So slide over here and notice, same base, same base. Nothing else down here, nothing else down here. So let's just isolate the exponents. 3 times x minus 4 equals x plus 6. And then now it's just a regular old algebra problem. You distribute the 3, you get 3x minus 12. And then now you add 12, you subtract x, 2x equals 18, x is 9. And if you're like, I don't know if I agree with that. Well, one, I don't know how you could disagree with my algebra here, but hey, that's fine if you're like, I don't know. Well, then take that 9 and plug it back in. 2 to the 3, 9 minus 4 power. Okay. Does that equal 2 to the 9 plus 6 power? Oh, interesting. So over here, this is 2 to the 15th, yeah? And then over here, that is 2 to the 3rd times 5. Well, pretty sure you're going to say that's 2 to the 15th. And now we're back to this scenario of, do you look at that and disagree with that? No, I don't think you do. So I don't think you'll disagree with that, those two being equal to each other either, right? Right. So the idea with solving exponential equations with the same base, is that you're looking at the powers, right? But they have to be, and this is a key thing here, the same base. If they're not the same base, that doesn't mean we're stuck. That doesn't mean we're at a dead end. In fact, you can go ahead and look ahead. Not the same base, not the same base. So we're not toast, right? So let's see what happens. Now, before we move on, I should point out that there is some wording down here that's like, hey, listen, b shouldn't equal 1, right? Because if it's 1, then it doesn't really matter what the exponents are, right? Because 1 to any power is going to be 1. And it also says they should have the same positive base. So positive base, and again, b doesn't equal 1, right? What if it doesn't have a positive base? Well, that's where it gets a little interesting, because like we've kind of said, what's negative 5 times negative 5? Well, that's 25. But what's 5 times 5? Well, that's 25. So you run into that kind of tricky scenario, but no need to worry. None of these are negative. None of these are negative because I'm trying not to be evil, right? Right. Okay. So these, all right, this is, like I said, where I would say, hey, why don't you try it? And I think you would fly through this. Like, for example, same base, ignore the bases, then x plus 1 equals 5. You don't even need to solve it. X is clearly 4, right? Over here, same base, but no exponent. What about the invisible 1, right? So 1 equals 2x minus 3. You add 3 to get 4. You divide by 2 to get that x is 2. Okay, yeah, that's not that bad. And if you're like, but wait, this is 1. How could the answer be 2? Well, think about it. You plug the 2 in there. 2 times 2 is 4. 4 minus 3 is 1. Over here, so 3x, 10x plus 3. Sorry, I really kind of jumped straight over the bases. Same bases, so just focus on the exponents. 3x has got to equal 2x plus 3, so x must equal 3. Again, if you're a little nervous about it, plug it back in. 3 times 3 is 9 here. 2 times 3 is 6 plus 3, that's 9. They're the same. Now, different bases. So all this means is you're going to mess with the bases. So 4 and 2, let's be honest, they're related, right? Because 2 squared equals 4. And maybe you see where I'm going with this. Let's rewrite 4 as 2 squared. Well, what did I leave out? Oh, the fact that that's true, right? So I have 4 to the x is 2 squared to the x power. And when you have a power to a power, that's 2 to the 2x power, right? And then on the right side is 2 to the 8th. And now you see, base is the same. Let's focus on the exponents. So x has got to be 4. Now, just by the way, this 4 has nothing to do with this. That's a coincidence, okay? Because the idea is if you took this 4 and went up here and did 4 to the 4th power, it would be the same as doing 2 to the 8th power. Now, I'm not 100% sure what that is off the top of my head. I think it's 256. Let's try counting. So 2 times 2 is 4, 8, 16, 32, 64, 128, 256. That's 4, that's 8. Yeah, it's 256 equals 256. Sorry, this was me counting like tally marks, by the way. Okay. I highlighted this earlier because I said, oh, look, different bases. But one of the things they're going to do is you're just going to think in terms of squares and cubes and things like that. You're just going to rewrite. They often, when we're in this form, are going to nicely rewrite each other, right? So if you're looking at this going, there's no way. Well, over here, didn't we just say 4 to the 4th was 256? We did. So really, we could leave this as 4 to the x and change this to 4 to the 4th, right? We said it over here. You could do that, but let's say you were like, you didn't see it. That happens, right? So maybe you go, well, you know what? This is maybe 2. So again, if me a second ago didn't help you, I'm going to write out a bunch of 2's and count it like this. 1, 2, 3, 4, 5, 6, 7, 8. There we go. So 2 times 2 is 4. Another 2 is 8. Another 2 is 16. Another 2 is 32. Another 2 is 64. Another 2 is 128. Another 2 is 256. And look, I've used all my 2's. So in theory, we could have rewritten this as 2 to the 8th. And we could have written this as 2 squared to the x power. And we would have, just like over here, I mean, literally very similar, right? 2 to the second power to the x power, you would get 2 to the 2x power, right? So check this out. Let's switch colors here. We would get 2 to the 2x power equals 2 to the 8th. You ignore the bases. You focus on the exponents. 2x equals 8. X must equal 4. Now, wait a second. Do you have to do this? No, check it out. We found that x equaled 4 right there, and now we have x equals 4 right here. Another one that I was like, oh no, different bases. But I think, do you automatically kind of see it? Over here, we were dealing with 2's in their powers. Okay, let's deal with 3's in their powers now, because 3 squared is 9, right? So take this 9 and whoosh, it's now 3 squared. But don't forget that 2x was its exponent, right? So it needs to be that guy's exponent. And then really this guy just drops down because now they're the same base. Actually, I guess with one little tweak, they'll be the same base because we're going to do this, 3 to the 4x power. Why is it 4? Because 2 times 2. That's it. Equals, in fact, here, I'm going to do that thing where I just grab this and bring it down here because boom, there it is. So we ignore the bases, so to speak. We focus on the variables. I guess focus on the exponents, sorry. Subtract x to get 3x equals negative 6. X equals negative 2. Wait a minute. Didn't I say something about we can't have negatives? I did, but don't get too freaked out. It's the base that needs to be positive, right? Didn't say anything about the exponents being negative. We can have negative exponents, right? So don't worry about that. In fact, if you really felt the need to, again, you could plug this in. You know, it would be 9 to the 2 times negative 3. Was it 3? It was 2. 2 to the negative 2 power. And that would be 9 to the negative 4th. Which, yeah, you could flip that if you just felt so you had to, but I'm not going to do that. So if you put a negative 2 here, you get 3 to the negative 2 minus 6. Well, that equals 3 to the negative 8th. And if you're like, see, they're not the same. But wait, remember, 3 squared is 9, and 2 times 4 would be negative 8. So, boom, we got it. It's negative 2. Okay. Interesting. These are different bases, but, you know, what are we going to have to do? Well, let's just change both of them. This is 2 squared. 4 is 2 squared. 8 is 2 cubed. And if you're like, oh, can we do that? Yeah, why not? This is still to the 3x power. This is still to the x plus 1 power. And all you're going to do is multiply the powers. So we get 2 to the 6x. And we get 2 to the 3x plus 3. How do I do that? You distribute, right? And then now we basically ignore the bases and we jump straight to the exponents to solve. You get x is 1. Okay, oh my goodness, we have a fraction. Don't freak out, because fractions can be flipped with a negative exponent. So we could write that as 3 to the negative 1 power, and then raise that to the x minus 1 power, right? And by the way, I kind of ignored this side of it because, I mean, hopefully it was a little obvious too that what we're going to be doing is manipulating these two to be the same base. Why? Well, because that's what we've been doing, right? Okay, so now what we can do is multiply these powers. So we get 3 to the negative x plus 1 power equals, now we could say 27, but we know that that is really 3 to the 3rd power, right? So what we do is we essentially ignore the bases. Negative x plus 1 equals 3. We subtract 1. And x is really negative 2. So now again, if I were here, I would propose this scenario and I would go, okay, solve it. And you would go, oh, okay, well, based off of our previous conversation of changing the bases to be the same, how would I do that? And I would say that's a good question, because the bases are clearly so funky. And so really, check it out below, I mean, literally right here, it's gonna do it for us. So we're gonna write a function. In fact, here, I'm literally just reading at this point. We're going to write a function to represent each side of the original equation. So, step one, this side is 2.4 to the x minus 1, and there it is. That's the left side. Step two is 5.76. There it is. And then they've graphed those both right here. So there's y equals 5.76. It's just a horizontal line. And then, as hopefully you were expecting, 2.4 to the x minus 1 power would look like that. If that's not what you were expecting, there's a couple ways we could have looked at this, right? So one is that, remember how we said that this right here is basically y equals 2 to the x power, and this would have been 1, because right here would have been the hiding initial value of 1, right? It's hidden in there, and if you're like, I don't know what he means by hidden, because it would technically look like that, right? And so there's our hidden initial value. Well, now that minus 1, where is it? Right there. That minus 1 technically just says, hey, we're going to move over. Remember? So, and if you're like, no, I don't remember. Okay, well, let me write it. A equals, not A equals, A times B to the x minus h plus k. Remember, this guy moves left and right. This guy moves up and down. Okay? And to help us remember that, remember I had a stupid saying of like, oh, this x is in jail, and you hate your x, and your hatred is with the x, and that's stupid, right? And then, oh, in jail, people are dishonest, so if you see a negative, it's actually positive. Okay, so let's go back and look at this. So there's a -1, so really, our initial value should be 1, right? Because it's 1 times 2.4. Let me zoom in. It's, look, 1 times 2.4 raised to the x power, but it's going to get moved to the left. I'm sorry, I screwed up. It's going to move to the right. So that's why that's 1 right there. See how that's 1 on the y-axis? And then it's a pretty normal, it's pretty close to our parent function, because look, our parent function was just 2 to the x. So, I mean, what do you think? 2.4 to the x can't be that much crazier, right? No, it's not. So, that's just step 1 was graphing this stuff, right? I'm sorry, really, step 1 was represent each. Step 2 is my favorite step, because it's use technology to graph the functions. Nice. And make sure to change the view so that you can see where they intersect. Okay? So I'm actually gonna pause the video, and, well, you know what? No, I'm not gonna pause the video because we have it right here. I was gonna say, like, do it and then be like, oh, look, there it is, but no. There was that line, there's this line, and they intersect at 3 when the y is 5.76. Well, that part should kind of make sense, right? And so, boom, once you have found the intersection, you have your solution is 3. So, how about doing this one? We're going to do all of this. Oops, we're going to do all of this to solve that right about now. So I'm going to zoom out and write it over here. So we have, hang on, let's just get rid of all this. Get rid of all this. so I don't have to move things around. Plus, we didn't really super need that information, right? All right, so we got 3 to the x plus 2 power equals x plus 1. All right, we take this part, y equals 3 to the x plus 2 power, and we take this part, and that is y equals x plus 1. So here's kind of the goofy part about this. We can graph this. This isn't that hard to graph. So first, the green one, x plus 1, that's super easy. The y-intercept is 1. The slope is 1. So it's just going to be go up 1 over 1, up 1 over 1, just like that. So let's graph that. Let me get a straight line tool. There we go. Straight line, like that. The other one, the purple one, our initial value would normally be 1, but it's moved -2, right? So here's what we're going to do. Move it over to, now it's going to be right here, okay? And then really just to kind of keep things here, I'm going to go ahead and pick some numbers. You know, like when x is -1, we get 3 to -1 plus 2. Well, that's 3 to the first power, so that's just 3. So here we go, 1, 2, 3, boom, right there. Let's see, when x is 0, we would get 3 to the 0 plus 2. Well, that's 9. So when x is 0, y is 9. Okay, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's right there. So I'm getting a little nervous. Are we actually going, will they intersect at all? Well, here's where we're going to go ask Desmos, because maybe they don't intersect, right? Maybe they are not equal to each other. So I'm going to pause the video, go grab Desmos. You can do the same. So, oh man, I was right. They don't touch. So the answer to this is there is no answer, because they can never be the same, right? No matter what I try and plug in, it's not going to work. So, like, let's just test that theory real quick. So, one, when we put in 0, well, we see that they're not going to touch at 0, right? So, okay, let's go back over here. So 3 to the 0, if we put in 0 there, 0 there. This is 3 squared, which is 9. And then the right side is 1. So does 9 equal 1? No, of course not. Let's go back over here. If we were to try -2, okay, so here's the line, -2. They're clearly not touching each other, right? So when we plug in -2, for this one, we would get 3 to the -2 plus 2. Well, that's 3 to the 0, which is 1. And if you plug in -2 there, -2 plus 1 is -1. Do 1 and -1 equal each other? No, of course they don't. So, for B, it is no solution. By the way, it's accidentally written there too, so no solution. And then this one is literally solved up there, right? And then I did kind of pull a slight trick on you. Here's B. Here's B down here. See, they don't touch each other. So, now we could do this one. Or if you feel like you've got this, then you can go to the big ideas. But if you're like, no, I think I'd like to see one more, then here we are. So let's try this out. 4 to the x minus 3 power, that's one equation. It's going to be red. And y equals 3x minus 8 is the other one. Well, you know what? This time I am just going to use Desmos to kind of speed up my life. I don't think you really care if I, the math teacher, can graph this rapidly or not on my own, especially when, look, step 2 is use technology to graph it. Okay, so I'm going to go do that. Ready, pause, here I go. So here it is. Check it out. This one, I don't know if interesting is the word that you would choose, but I think it's interesting. So look, there's my 4 to the x minus 3 power, 3x minus 8. They don't cross once because they cross twice there and there. So that means there are 2 solutions to this one. If x equals 4, there's a solution, and if x equals 3, how can this be? Well, let's plug them in and check it out. So what was it, 4 and 3? Yeah. So if x is 4, we get 4 to the 4 minus 3 power, and that's 4 to the first, which is 4. Okay, that's the left side. And if we put 4 over here, 3 times 4 minus 8. 3 times 4 is 12, 12 minus 8 is 4. So yeah, that works, right? Okay, let's slide over and try 3 now. So if we do 4 to the 3 minus 3 power, well, that's 4 to the 0, which is 1. And now if we plug it in here, we plug in 3, we get 3 times 3 minus 8. Well, that's 9 minus 8. That's 1. Oh my gosh. They both are the same. So it's crazy. Yeah, there are 2 solutions. I shouldn't say crazy. I just like stuff like that. That we just had an example of 1 solution, no solutions, and then 2 solutions? That's crazy. So hopefully you stuck around and watched the video for that. If you didn't, oh well. You have a big ideas assignment over this stuff, over solving exponential equations. Let me know what questions you have. I'll see you later.